Welcome to Maths with Bob. Today we're looking at a bit more algebra, and we are doing a bit of a continuation of the index laws, and we'll be looking at products and factors. But these 4, 5 and 6 are basically the other three index laws. Now a to the minus n equals 1 over a to the n. These create fractions. Like for instance, if I had say 5 to the minus 1, that's equal to 1 over 5 to the power 1. So some people would say that 1/5 could be written as 5 to the minus 1. So you could also do it the other way. Say I had 1/4, I could rewrite that as 4 to the minus 1. Okay, so I can actually say that the fractions can be written as negative indexes, or if you like, the negative indexes create the fractions. Say I had say 5 to the negative 2. Okay, that's actually 1 over 5 squared, or if you like, 1 over 25. Okay, so you can see that you can actually use this in reverse. Say I had, so I had 1 over 8. Okay, 1 over 8, which is really, you might hopefully see that. That's actually 1 over 2 cubed, so it's actually 2 to the negative 3. Okay, these are the negative indexes. They actually create I think the easiest way to think of them is create the fractions, or if you like, the fractions can be written as negative indexes. Now, index law number 5 is the fractional index one. Say I had 8 to the 2/3. Now I've got to take the cube root of 8. I think the easiest way is to look at the bottom number, take the cube root, so it's 2 squared, squared, which is equal to 4. Okay, so if you like, let's try another one. Okay, so I had 27. Okay, so I had 27 to the 2/3. Now the bottom number is the root number. I always think of it like that. So I'd actually have to find what's called the cube root of 27 and square it. So let's try that one. Okay, so 27 to the 2/3. The bottom number is the root number, so it's actually 3 squared, which is 9. Okay, so 27 to the 2/3 is actually, okay, the cube root of 27, 3 squared, and that's, you can see here, 9. Now you can combine these as well. Say I had, let's have a look, say 8 to the minus 2/3, typical one. That's really 1 over 8 to the 2/3, which is 1 over 4. Hopefully you can see cube root of 8, 2 squared is 4. So I can combine the negative and the fractional indexes together. Okay, so let's actually have a look at some examples. Just before we go on, the last index law, a to the power 0 equals 1, is just, I guess, one that actually creates or makes a lot of the algebra work, actually, and we'll have a look at a quick example. Suppose I had 5 lots of a to the power 0. That's actually going to be 5 times 1. Okay, so that should be equal to 5 times 1 if that was a to the power 0. Okay, all right. I've got to watch the zeros. They create little dots. Okay, so let's actually do some examples. Okay, let's have a look at some examples. How about we had 64 to the power 2/3 plus, say, 32 to the 3/5. 32 to the 3/5. Okay, now, obviously we've got to take the cube root of 64, which is 4, so that's going to be, what, 4 squared? 4 squared. And then the 5th root of 32 is 2, so it's 2 cubed. Okay, we can see here this is just going to be what? 4 squared, 16, so it's going to be equal to 16 plus 8, which is 24. Okay. Now I can, if I actually have algebra expressions like, let's have a look, say I had a to the 2/3 times, say, a to the 3/5. Well, obviously what we do in this case is we just add the indexes because the bases are the same. Okay. Let's actually look at some combinations with negatives as well. So let's actually do some negative examples. Okay, so I had 2 to the negative 2, okay, plus 3 to the, say, negative 3. How would I do that? Well, that's just equal to, you can see here, 1 on 2 squared plus 1 on 3 cubed. You can see that's basically 1 on 4 plus 1 on 27. So it's equal to 1/4 plus 1 on 27. Okay, 27, which is equal to, what's that, about 31. Okay, over 4 27s, 5,408. Okay. All right. Okay, well, let's actually have a look at some of the ideas of products and factors next. Right. This should be 24 over there in that column. Let's actually have a look at a bit of algebra with this. Okay, I'll just rub some of these things out. Okay. Let's actually have a look at, say, a to the, say, 2/3 times, say, a to the -5. Now, if I have an algebra expression like this, we can, as you can see, we just add the indexes. So it's just going to be, what, a to the power of, what, it'll be 2/3 -5, so it'll be actually -4 and 1/3. Okay, so we can just deal with the fractional and negative indexes just like normal indexes and use our index laws. You know, the a to the m times a to the n is equal to a to the m plus n. And if we actually had a subtraction, like say we had a to the 2/3, okay, divided by, okay, a to the -5. You can see here this would be a to the power, okay, it'll be 2/3 -5, so it'll be a to the 5 and 2/3. Okay, all right. A to the power 0, 1. Let's just do a quick one. Say I had 5 lots of a to the 0 plus 3 lots of a to the 0 plus 2 lots of b to the 0. B to the 0. Now, you have to be a little bit careful here. That's 5 times 1 plus 3 times 1 plus 2 times 1, which is just 10. Okay, okay, just be careful with those ones. Okay, well, let's have a look at this idea of products and factors, and what is a factor and what's a product. I always like to think of them as the algebra with brackets. So if I want to factor something, I would put brackets in, and if I want to find a product, I normally expand it out and get rid of the brackets, you could say. Okay, so let's have a quick look at an example. Suppose I had, say, a squared b plus 3a. Now, the general idea, okay, well, I've got two terms. What could I take out as a common factor? Okay, so I just look at each individual term, and then I see basically I take the lowest power out usually, and I'll just say, okay, can I take any numbers out? No. Can I take a b out? No, it's not common to both of the terms. A, yes, I actually could take an a out of both, and then I can see what am I left with, okay, to recreate the term a squared b. Well, it'll just be an AB. How about if I take an a out of the 3a, what would I need to recreate the term 3a? Or just a 3. So you can see I've actually now factored this expression with two terms in it into a lots of ab plus 3. Now if I expand this out, basically, I should get back my original two terms. Okay, so basically what would happen is, if I expanded it out, remember, I just undo this, so I multiply this one by this one, and so I just multiply these things together. Okay, so I just go a times ab, which should be what? A squared b, and then, okay, a times a 3 is just a 3a. Okay, so you can see they are sort of working in reverse. If I factor something, I actually take something out of each of the terms and put it on the outside of a bracket, and if I expand something, I basically eliminate my brackets. So actually So we're going to look at some harder examples of this shortly. Okay, well, let's actually make up a product. Let's say we have like 3x minus 2y times, say, 5a. Let's do a simple 1 minus, say, 2 or something. Okay. Now here we have what's called a binomial product. We've got two brackets multiplied together, and a lot of people use this idea of FOIL. FOIL was the idea of this one times this one times this one, and then this one times this one, and then this one times this one. Okay, this is the FOIL way of multiplying out a double bracket. But what I'm going to suggest we do, or how we do these ones, is always just take the first term, okay, in the first one. Let's have a look. What would that be? That would be this one here. Okay, so we take the 3x. Okay, so let's take the 3x. Okay, and we multiply that by the whole second term over here. Okay, this one here, 5a minus 2. So we rewrite that as 3x times 5a minus 2. Okay, then we take the second term, okay, in the first bracket, which is this one here, the minus 2y. We use its sign as well. Okay, so we write down minus 2y, and then we put a bracket, and we multiply it by this, this term here again. Okay, which is, you can see here, just obviously 5a minus 2. So we already have what's called a common factor. We expand it out using 3x times 5a minus 2 minus 2y times 5a minus 2. When we expand this out, we will get what 3 5s are 15ax minus 2 3s are 6x minus 2 5s are 10ay. 10ay. And then minus 2y times a minus 2 is a plus 4y. Okay, now if you look at this, if you actually go backwards, this is actually called grouping in pairs. So if I look at this last term here, this one here, this big term expression here, I look at that and say, how could I factor that? Well, going backwards, you can see, well, we've actually factored this one here, okay, is in fact this one regrouped, okay. And if you have a look at this one here, okay, if I work backwards, you can see here, you now have that one regrouped, okay, and then we put it back into what's called the binomial product like this. So when I actually do an expansion of a double binomial product this way, it's actually what's called like grouping in pairs in reverse, and it gives you a bit of an idea of how to do what's called a grouping in pairs factoring. Okay, well, let's actually look at some common factoring ideas. Well, the first one, the first usual one, is the difference of two squares, like a squared minus b squared. Okay, this is equal to, hopefully we all know, a plus b times a minus b. Let's look at a quick example. Suppose I had, say I had x squared minus 9. Okay, typical one, this one. Okay, we can just see this is just x plus 3 times x minus 3. It's not too bad. Okay, how about we had, say, 8y squared minus 64m squared. Okay, hopefully we can see, we just take the square root of this, what do we get? Square root of 8. Okay, it will be 2 root 2. Okay, so it will be 2 root 2y. Now, minus, okay, that's 8m. Okay, and what's the square root of 8? Okay, 2 root 2y, now plus 8m. Okay. And sometimes you actually need to take out factors. Okay, so you may have to take out a common factor. We could probably take out, we could have taken out an 8 out of this one. Let's have a look. 8 lots of y squared minus 8m squared. We could have actually done it like this, and then say this is really 8 lots of, now just y minus, now again we've got the square root of 8 again, which is, okay, 8 to the power of half. Okay, which we could break up, okay, which is just 2 root 2, and then again we have a y plus 2 root 2. Okay, okay, let's have a look at the next one. Okay, let's rub this out. Okay, okay, let's go on to the difference of cubes now. We'll just, so we know, have a look. How about a cubed minus b cubed? Now what's that? Well, this is a new one, depending on what level you're at. This is a minus b and then it's going to be a squared plus ab plus b squared. Okay, let's just have a look at a few examples. Okay, suppose we had, say, well, let's do y cubed minus now 27n cubed. Okay, so we just see this is going to be what? Now the cube root of y is just, it's going to be just y minus 3n at the front. Then it's going to be, okay, y squared here. Now it's going to be plus. Now 3, it's just going to be 3ny here. And then the last one will be just okay, b squared, which will in fact be what, 9n squared. Now how did I get those? Well, if you look at each of these, okay, this one here, okay, y cubed, hopefully we can see that that is in fact the y, so the cube root of that one is y. How about this one? What is the cube root of 27n cubed? Okay, that obviously hopefully isn't at 3n. So really what's happening here is we're saying that, if you like, a is equal to y and b is equal to 3n. You can just see if you actually plug that in. A times b is 3ny, and you can see that over here. Okay, this is the 3ny. Okay, so you just have to fit them to the formula. Sometimes you may need to fiddle and take the cube roots of the expression. Sometimes you may need to take out factors, and perhaps we should actually have a look at an example of one of those. Okay, well we'll just rub this out, and let's just have a look at another example, one where you need to take a factor out. So you had something like 40p cubed minus 320 q cubed. Now we can take out actually a 5 out of each of these, so we get 5 lots of 8p cubed, and then we get a minus, I think, 64q cubed. Okay, so we can then write that as basically 5 lots of, now what is a? Okay, so a now becomes what? So a would be equal to the cube root of 8p cubed, which would just be 2p. And how about b? Now that would be the cube root of 64q cubed. Hopefully so that's 4q. Okay. So when we put it into the formula, okay, so it becomes what? A minus b, so it's going to be 2p minus 4q. Okay. Now a squared, okay, that's going to be what? 4p squared plus, okay, now ab, which is 4 2s are 8pq, and the b squared is just the 4q squared, which is 16q squared. And then we have it factored. Sometimes you might like to, as you can see, take out a common factor before you try and factor them. Okay, let's have a look at the next one. Well, the next one is the other cubic factorization. Okay, you can see here it's going to be a plus b at the front, and then we have a squared minus ab here, plus b squared. Okay, very similar to the other one, but you can see the minus sign is now moved into the second bracket. Okay, I always like to think that if it's a cubed plus b cubed, the a plus the b is at the front, and if it's a cubed minus b cubed, the a minus the b is in the front bracket. So let's have a quick look at an example. Okay, suppose we had, say, something like x cubed plus 125, okay, r cubed. Okay, so you can see here, well, what's a? A is just, if you like to think of it like this, what is a? A is just x, and what's b? B is just the cube root of this, which is, you can see here, just 5r. So what would happen in the first bracket? You just have what? A plus b, which is now x plus 5r, a squared, okay, which is just x squared, Now it becomes minus AB, so it's minus 5rx, and then plus b squared, which is 5r squared, which is 25r squared. Okay. All right. Okay, let's have a look at another example where we need to take out a common factor. Okay, let's have a look at one where you need to take out a common factor. I'll just rub this out for a second. Be a bit careful here. Okay, so let's actually have a look at one. It's a fairly big one. Say 432t cubed plus 686 u cubed. 686 u cubed. Now, I'm just going to take out a 2 to start with, and hopefully, let's have a look. 2 times now 216 t cubed plus 343 u cubed. Now, you may not recognize these as cubes, but the cube root of 216 is actually 6, so a is going to be equal to what? 6t, and what's b is equal to eventually, what's that, 343, so I think that's 7u, with a 2 at the front. Okay, so let's have a look. How will we do this one? Well, we just say it's going to be 2, lots of now a plus b, which is going to be 6t plus 7u, then a squared, which is 36, there's supposed to be a 6 there, 36 t squared. Now we have a minus, okay, so we have a minus AB, so 6 sevens are 42 TU, minus 42 TU, and then the last one would be the B squared on the end, okay, which C, which is 49 U squared, 49 U squared. Okay, there we have the A cubed plus B cubed, a few examples. Okay, let's move on. Now, just before we move on to a to the power 4 minus b to the power 4, what if I have a squared plus b squared? Okay, we can't actually factor this in the real number system, and if you do a bit of work on complex numbers, you'll realize that, okay, this is going to be just a plus ib times, okay, a minus ib. Now, this is where I is equal to the square root of -1. Now, but this is in the complex number system, okay, so there's no factoring in the real number system, so I'll just write that. We can't actually factor this in the real number system, so let's just rub this out. Okay. No factors, okay, in the real number system, in the reals. Okay. No factors in the reals. Okay, so let's go on to another one. How about a to the 4 plus b to the 4? Okay. Now we can't actually factor that one either, for that matter. So there's no factors for this one. Okay. How about we take out, say, let's do a to the power 4 minus b to the power 4. Well, we can actually rewrite this as a squared minus b squared, and we can sometimes do this and help us. We can say this is a squared plus b squared, which we can't factor, and then a squared minus b squared, which we actually can factor. So we can sometimes break these down a bit. A squared plus b squared, okay, a plus b again, and then a minus b. Okay. Well, this is most of the common factors. After a to the power 5, b to the power 5, we can't factor them. So we can normally do up to a cubed. You can see here we can do the a to the 4 one, but we can't do a4 plus b4. Okay, we'll just pause for a second. Okay, we're now moving away from basically putting brackets into actually removing brackets, so we're actually expanding out what's called products. Now, Pascal in about 1600 came up with a lovely triangle, okay, which is used in lots of areas, but basically it starts off with 1, 1, 1, and then we add the 1 and 1 and we put the 2 underneath, and we keep on putting the 1s on the outside. So 2 and 1 is 3, 2 and 1 is 3, with the 1s on the outside. Okay, 3 and 1 is 4, 3 and 3 is 6, 3 and 1 is 4, 1, 1. And then I'll just go one more, 10 here, you can see 5 and 5 and a 1 on the outside. Now, these actual numbers in each row are the actual coefficients. So if I picked this one, the 1, 2, 1 are for the expansion of a plus b squared. So if you like, this is let's have a look at a plus b squared would be what? The first one is 1. Now it's 1a to the maximum power. So it's 1a squared. Now plus, now it becomes 2. The a drops down a power and the other number, or the other letter comes up. So it becomes 2ab plus, okay, now the b will come up 1 and the a will go down to 0. So we end up getting 1 lot of a to the 0 times b squared. So it's just actually b squared. So you can see here the 1, 2, 1 are in fact the coefficients of the terms, okay, and the 1, 3, 3, 1 are the coefficients of a plus b to the power 3, and I'll just write that down. So it would be a cubed plus 3. Now the a drops down, a squared. The b will start to come up to 1. You could say it was originally 0 in the first term if you wanted to. Then you can go 3 lots of a will drop down, b comes up to another power, so b squared, and the 1 on the end would be what? B cubed, 1 lot of b cubed. Okay, let's look at the next one. Okay, this would be, a4 plus 4a cubed b plus 6a squared b squared plus, what, 4, a is dropping down to just ordinary a b cubed, and right on the end would be a plus a b to the power 4. Okay. And if we want to do the last one, 5, let's actually do the last one. So it'll be what? We're running out of room there, so let's write it underneath. So it'll be what? A to the power 5. So this is going to be the expansion of a plus b to the power 5. So it'll be like a plus b to the power 5. Okay, those are obviously the ones above. 1, 3, 3, 1 is a plus b all cubed, and 1, 4, 6, 4, 1 is a plus b to the power 4. Okay, so this is 1, 5, 10, 10, 5, 1, which is a plus, well, are the coefficients of the terms in the expansion of a plus b to the power 5. Okay, and this is all related to what's called the general binomial theorem, and there's a fair bit of work on this later. But we're just going to use Pascal's triangle now just to give us the actual, well, help us expand the brackets to higher powers than 2 and 3, and we're just going to use the actual numbers to give the coefficients. So here we have 1, now the 5, okay, the a would drop down to power 4, the b would start coming up, we're then getting a 10, the a is dropped down to a cubed, the b's come up to b squared, we get a 10 again, the a is now dropped down to a squared, the b's come up to b cubed, the 5 is now, this is the second last term here, which is now a b to the power 4, and the last term 1 in the b has come right back up to 5. Okay, so let's actually use this in an expansion. Okay, so let's actually just first of all let's actually just rub out some of these. Okay, I'll just rub out some of these, and we'll just use the last one. Okay, I might actually rub it all out. Hold on. Okay. So we know for something like a plus b to the power 5, the coefficients were 1, 5, 10, 10, 5, and 1. Okay, now we can actually use this as quite a powerful idea. If we had, say, something like, let's have a look, 7x on 3 plus minus 2 on 3q or something like this, all to the power 5. Well, what's happened now is that in fact we've now let's make that negative. So I can actually make a and b positive or negative. So how about I actually make that a negative there. So really what's happening now is that a is equal to 7x on 3 and b is equal to minus 2 on 3q. So when I actually want to expand that out to the power 5, I can just do the substitutions into these expressions. So we know that the expansion would be something like, in terms of a and b, we know it would be a to the 5. Okay, there's a fairly long one here. Okay, B starts coming out down to 10. Okay, so actually I'll just write it out. Okay. Okay, write an n plus what, b to the power 5. Okay, so what would happen now is whenever we saw the let's have a look. So this one here, okay, would now go in wherever I saw an A. So it goes into each of, okay, these, wherever I see an A, okay, all right. And then the B, obviously, this one here, okay, this one, okay, being negative, okay, would then go into wherever I saw a B. So it would go into here, 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 obviously here, and right over here. So obviously the terms would start oscillating because obviously if B is negative, B squared is positive, and B obviously to an odd power would in fact be negative. So the terms would start to oscillate in sign. So you can see you can actually use this idea by substituting, just getting the general expansion for A plus B to a power, and then substituting particular values in for the A and the B, and we can be used quite as a powerful tool for larger expansions. Okay.